All right, let's talk about machine learning. We're going to pull back the curtain today, move past all the buzzwords and the hype, and really look at what it takes to go from a simple idea to a real-world, working solution. It's a journey, and we're going to walk through it step by step. Let's dive in. You know, this whole idea of smart machines, it's not new. Not at all. It really got its name way back in 1956 at Dartmouth College. A bunch of researchers got together, and they had this radical idea that you could describe human learning so precisely that a machine could do it too. For a long, long time, it was mostly just that, an idea. But then, something changed. The explosion of big data and computers that are just unbelievably powerful, that was the rocket fuel this old idea needed to finally take off. Okay, so let's clear up some of the lingo, because you hear these terms thrown around all the time. Think of it like this. Artificial intelligence, or AI, is the big dream, the whole universe of making machines smart. Now, inside that universe, you've got machine learning, or ML. That's a specific approach to AI where, instead of writing a ton of rules, you just feed the machine data and let it figure out the patterns on its own. And then, a subset of that is deep learning, which uses these really complex, brain-like structures to solve even harder problems. It's like one of those Russian nesting dolls. Deep learning is inside machine learning, which is inside AI. So that's the million-dollar question, isn't it? How does a machine actually learn? It sounds like some kind of magic, but I promise you the basic idea is something we all understand. It really just comes down to learning from examples. Let's take a super common example, detecting credit card fraud. Now, the old way would be to write a bunch of if-then rules. If the amount is big and it's late at night, then flag it. But with machine learning, we don't do that. Instead, we just show the machine a massive list of past transactions. And this is the key, for every single one, we give it the answer. We tell it, this one was legit, this one was fraud, this one was legit, and the machine's job is to stare at that data until it finds the patterns that lead to that final answer in the is fraud column.
Yeah, that is fraud column, that's the absolute secret sauce. In the biz, we call it the target variable, or sometimes a label. It's basically the cheat sheet. It's the answer key we give the machine so it can start connecting the dots between the transaction details, the amount, the time, and the final outcome. Without that known answer, the machine has nothing to learn from.
And this whole approach, where you give the machine data that already has the answers included, well, that's a perfect example of the most common type of machine learning, which is called supervised learning. It's supervised because we're supervising the process, guiding it with that labeled data. Our fraud example is what's known as a classification problem. We're trying to put each transaction into a category, fraud or not fraud. Now, if we were trying to predict the exact dollar amount that might be stolen, that would be a regression problem, because we'd be predicting a number instead of a category. Okay, so we've got the basic idea. The machine looks at examples with answers and learns patterns. Easy enough, right? But here's where so many people get it wrong. Building a real-world machine learning system isn't about just picking some super fancy algorithm and hitting the run button. It's actually a really disciplined, structured process.
So what does that process look like? Well, the industry standard blueprint is called CRISP-DM, and you'll notice it's a loop, not a straight line. It all starts with the most critical step, business understanding. What are we actually trying to achieve here? Then you get into the data, you explore it, and then you hit step 3, data preparation. Honestly, this is almost always where you spend most of your time. Cleaning messy data, getting it into the right shape. It's only after all that work that you get to the fun part, modeling. And from there, you evaluate it, you deploy it, and boom, you're often right back at the beginning with new questions.
And this really is the key takeaway here. The source material says it perfectly. The algorithm itself is just part of a larger process. You can have the smartest, most powerful algorithm in the entire world, but if you're feeding it garbage data, or if you haven't clearly defined the problem you're trying to solve, you're going to get garbage results. It's that simple. So, speaking of getting garbage results, this whole journey is kind of like navigating a minefield. There are a lot of ways it can go wrong. But two of the biggest, most common pitfalls, well, they're really just two sides of the very same coin.
It's a balancing act. On one side, you've got overfitting. This is like a student who doesn't learn the material for a test, they just memorize the exact answers from a practice test. They'll ace that practice test, sure, but give them a new question, they'll fail miserably. The model memorizes the past instead of learning the rules. On the other side is underfitting. This is where the model is just too simple. It doesn't even learn from the practice test. It fails on everything.
Now, there's a technical term for this balancing act. It's called the bias-variance trade-off. Think of it this way. A model with high bias is too simplistic. It makes broad, sweeping assumptions, and that leads to underfitting. A model with high variance is the opposite. It's way too complex and jumpy. It pays attention to every little bit of noise in the training data, which leads to overfitting. The real art and science of machine learning is finding that perfect sweet spot right in the middle.
So how do we actually find that sweet spot? Well, one of the most important tools in the toolbox is a technique called cross-validation. It's a pretty clever idea. Instead of using all your data to train the model, you chop it up into, say, 5 chunks. You then train the model on 4 of those chunks and use the last chunk, the one it's never seen before, as a pop quiz to see how well it performs. Then you repeat that process with a different chunk held out for the test. Doing this over and over gives you a much better sense of whether your model actually learned the general rules or if it just got lucky.
Okay, I know what you might be thinking. This sounds incredibly complicated. A 6-step process, balancing bias and variance. But here's the really good news. We live in an age where there is an amazing set of tools that makes this entire journey so much more accessible.
First up is the software. We have these amazing frameworks that do a lot of the heavy lifting for us. You have things like TensorFlow, which is super powerful and gives you control over every tiny detail. But then, built right on top of it, you have something like Keras, which is designed to be simple and fast. It lets people build unbelievably complex models with just a handful of lines of code. It's a total game changer for moving quickly from an idea to a working model.
But all that amazing software needs some serious muscle to run on, and that's where hardware comes in, specifically graphics processing units, or GPUs, mostly from NVIDIA. These things are the absolute engines of modern AI. They're designed to do thousands of calculations all at the same time, which is exactly what you need to train a big model. And the special sauce that connects the software, like TensorFlow, to the hardware is a little thing called CUDA. It's the translator that lets them speak the same language.
And here's maybe the most exciting part of all. You don't need to build a supercomputer in your garage anymore. All of this power, it now lives in the cloud. Companies like Amazon Web Services offer these incredible services like Recognition for understanding images or Lex for building chatbots. They've already done the hard work of training these massive models, and they let you just use them. This has completely democratized machine learning, putting it in the hands of basically everyone.
So if you're going to walk away from this explainer with just one thing, let it be this. Machine learning isn't a magic algorithm in a black box. It's a structured engineering journey. It's a process that starts with a real-world question and ends with a real-world solution. The algorithm? That's just one small, though important, piece of a much bigger, much more fascinating puzzle. And that really brings us to the present. We've gone from a theoretical idea in the 1950s to a world where these incredibly powerful tools are available to anyone, literally just an API call away in the cloud. Which leaves us with a pretty exciting question to think about. With all this power at your fingertips, what problem would you teach a machine to solve first?